right, we're live on YouTube, and
Right.
let's wait. Let's get started at 3 sharp.
I don't think I've ever been on YouTube before.
I don't think we have enough views to make money out of it. I'm not sure that would be ethical either.
You hear about people crowdfunding their research, right? So.
Oh, that's an interesting possibility. All right, so it's 3 o'clock. Let's get started. Welcome back, everyone, to our Quantum Matter seminars. And it's my pleasure today to introduce Steve Johnston from the University of Tennessee at Knoxville, who's going to tell us about his work together with experimentalists on realizing unconventional superconductivity on silicon surfaces. Please, Steve, go ahead. By the way, feel free to interrupt at any time if you have questions. Just unmute yourself, or you can post your question on the chat as usual. Thank you.
Okay. Adrian, can you keep an eye on the chat if something comes up there, because I'm not going to be able to see it. All right. So yeah, thank you everyone for coming. So today I wanted to take this opportunity to tell you a little bit about some recent work I've been doing in collaboration with my experimental colleagues here at the University of Tennessee. And in particular, it's looking at the discovery of what we think is unconventional superconductivity in a tin monolayer system grown on a silicon substrate. So today I want to go over some of the evidence for that, and in the end try to convince you that this system is really a chiral D-wave superconductor. So before I begin, I want to, as I said, this has been a collaboration, and I want to start by acknowledging my colleagues who've been working with on this. So the experimental efforts have been really driven by Hanno Weitering's group, the department head here at Tennessee. And his postdoc, Feng Ming, is the one who actually led a lot of the experiments that I'm going to be showing you during the talk. I want to say that this system that I'm going to be describing today, Hanno has been working on this for 30 years now. He started this work with Ward Plummer back in the early 80s. It's got a really long, interesting history, and he's got a really nice talk on it. So if you're looking for a speaker down the line, I would really recommend that you invite him to come tell you a little bit about the journey to this work. The theory was done in collaboration with my collaborator, Thomas Meyer at Oak Ridge National Lab, and a postdoc that we're sharing through a SciDac program. So Pai-Z did a lot of the DCA calculations that I'll show partway through the talk. And of course, this work is supported by some grants from the Office of Naval Research, the US Department of Energy, and the computing time is awarded through an Insight Award. Okay, so here's the outline of the talk. I'm going to start by introducing this tin silicon adatom system. And I want to present some of the evidence that we have that this system is really can be treated, or it looks like has the hallmarks of a Mott Insulator that can be doped. So I'm going to talk a little bit about the system itself, how we achieve the doping levels and whatnot. A lot of the theory evidence that I'm going to be discussing, or the theoretical work, is based off quasiparticle interference. So I'm going to talk a little bit about what this technique actually measures, talk about how we model it in relationship to the system. And then I'll go through some of the results we have for this quasiparticle interference that leads to really I think some of the smoking gun evidence that the system is indeed a doped Mott Insulator. And in the last quarter of the talk, I want to talk a little bit about some very recent results that we've got that we're sort of in the process of writing up, which is really the evidence that the system is a chiral d+id superconductor. Okay, so these monolayer systems that we're talking about, in this case, it's a third of a monolayer of tin deposited on the silicon 1,1 surface. So there are a number of these adatom systems where you can deposit a third of a monolayer onto silicon and germanium substrates. Lead is an example, tin is another example. The atoms will arrange themselves in these really nice triangular lattice structures that are separated by several lattice constants on the silicon surface. And so what happens is that the silicon 1,1 surface has these dangling bonds that it wants to passivate. And so the sp bonds of the atoms will bind to the surface. They'll create a covalent bond with the surface and leave sort of one half-filled dangling bond pointing perpendicular to the surface. In the case of tin, what happens is you get one electron per orbital. The orbitals are pointed perpendicular to the surface, and they're separated by quite a large distance. And so the orbital overlap between these dangling bonds is actually quite small. So they're a very narrow bandwidth system. And it turns out that that bandwidth actually becomes comparable to the Mott-Hubbard interaction that you would calculate for that dangling bond. That's really what we think drives the Mott physics. So in the parent system, these can be grown in these really nice surfaces covering very large air volumes. So this is a topographic map of the undoped system grown. You can see it's a really nice triangular lattice. These black dots correspond to tin vacancies, but they're very pristine samples, and they have this really nice sort of flat surface. There's not really much evidence for rippling. This is different from lead atoms on the same surface. The lead atoms on the same surface actually undergo a series of interesting charge ordering and CDW type transitions, which is another interesting subject, but I'm not going to talk about it today. So as I said, these systems have long been recognized as potential Mott insulators, again, because of the very narrow bandwidth and the very weak orbital overlap between these dangling bonds, these dangling orbitals. And so, people have been interested in them for quite some time. And there was this nice theory experimental paper from Werner Hanke's group, came out in 2013, where they actually looked at the electronic structure for these systems. And what they found is with DFT calculations, indeed, you get the tin atoms form this nice single band with a bandwidth of about half an eV that passes through the Fermi energy. DFT predicts it's a half-filled band, as you would expect by just counting the orbitals. But what they found is that when they calculated the U and then inserted that into a DFT plus DCA calculation, they found that the U was sufficient to open a gap in the system. And so, this is, again, expectation, or this is what you would expect for a Mott insulator, for example. And just for reference, this is what the Fermi surface looks like for the undoped system in DFT. I'll come back to this a little bit later. So in this paper, they then went and compared against RPES measurements. So this is what's shown here. So A and C, these correspond to actual RPES measurements along certain bonder or certain high symmetry cuts. And you can see, again, you get this, what looks like a very broad, weakly dispersive band that's got a gap separated from the Fermi energy. This is what we would normally associate with a lower Hubbard band. This persists along both momentum cuts. And then in comparison to this LDA plus DCA calculation, they found that there was really good agreement. And they argued that this was really, indicative of a Mott insulator or a Mott insulating phase in the system. They also discuss a little bit of evidence they have for some zone folding here, which they link to magnetism, but I don't want to go into too much detail about that here. Sorry, I thought it's, so just for reference, I can't see it here underneath my own little window here. So again, the U is on the order of about 66 MeV or 660 MeV, and the bandwidth of the system is about half an eV. So again, U over W is order 1, which again places it squarely in this Mott insulating regime. So yeah, this paper came out. They were arguing that the system is indeed a Mott insulator, but then of course there were a number of other proposals that came out saying, well, no, wait, the system could be a Slater insulator. There were a number of proposals for different magnetic orders that can be realized in the system. So for example, you can have this anti-ferromagnetic row-like ordering occurring. There are these spiral 300 or 120 degree anti-ferromagnetic orders that have been proposed. And there's been these ferrimagnetic orders that have been proposed. And this paper here from this PRB was essentially arguing that no, the system's not really a Mott insulator. It's more likely probably a Slater insulator. And the insulating properties are being driven by the magnetism. So this is where the work with Hanno came in. We wanted to try to isolate or try to determine really, is this in fact a Mott insulator? And so the way that we wanted to do this is to look at how the system is doped, right? How does the gap collapse as a function of doping? So this is really driven by sort of the notion that when you dope a Mott insulator, the way that the spectral weight rearranges itself is very different from when you dope, say, a band insulator or something like a Slater insulator. So to remind you, I'm going to go through this sort of
just a short question.
Go ahead.
Well, you said it could be a Slater one, but isn't it true that usually magnetism comes in at much lower temperatures than the scale of the Mott gap? So isn't it true that by raising temperature, you can always distinguish between a magnetic order as being...
Yeah, so the problem with that in this system is that when you raise the temperature, the atoms actually start to disassociate from the surface before you reach the temperature scale of the Mott transition.
Oh, I see. Okay.
And so doing it with temperature is not really a good way to go about it in this particular system. Okay. And it just has to do with the chemistry of the surface. Yeah.
I see. Thank you.
Yeah. So to remind you, in a band insulator, what you expect to have happen is you're going to have bands with spectral weight 2n. If you have n atoms in the system, there will be a filled band with spectral weight 2n, a gap to an empty band with a spectral weight of 2n, and a Fermi energy located between the two. And when you dope the system, remove electrons from it, we get these sort of rigid band pictures that we talk about in solid state physics classes. You remove some of the spectral weight and the Fermi energy or the chemical potential just swings down into one of those bands. This is very different from what happens in a Mott insulator. So in a Mott insulator, you're expecting to have on average one electron per site. And so if you ask how many ways can I remove an electron from the state, well, there'll be n ways you can do that. There is another n ways you can add an electron to the system, but that'll cost you u, and so you'll get a splitting of the spectral weight n occupied states below, n occupied states below or above the Fermi energy, and they'll be separated by a distance of about the Coulomb interaction, or the Hubbard interaction, sorry. When you dope the system, though, you can do the same counting argument, and what you find is that, again, there's n-1 ways now to remove the electron, if I've taken one electron out of the system already. There are n-1 ways I can add an electron, again, at an energy cost u, but I also introduce 2 ways that I can add electron, either a spin up or a spin down to this empty site, and that costs me almost no energy relative to the occupied states. And so what happens is you get this sort of quasi-particle-like spectral weight forming here, which pulls its weight sort of equally from the upper and the lower Hubbard bands. And you expect the same thing to happen with electron doping. It's just which Hubbard band your quasi-particle peak gets tied to shifts. So this is a very old argument from Sawatsky and Eskis. I refer you to this paper if you're interested. This, of course, we can confirm this with quantum Monte Carlo calculations. So this is actually work that I was involved in as a PhD student, and Richard was involved in as well. This is spectral functions computed for a 2D Hubbard model on a square lattice done with determinant quantum Monte Carlo. So it's shown here, this is the energy versus momentum. And you can see here, we've got sort of a lower Hubbard band that's very broad, well below the Fermi energy. I've got a gap of states, and then I've got another upper Hubbard band sitting up here, and these correspond to these n addition and n removal states that I had in this sort of cartoony picture. When we dope the system in the calculations, what we find is that spectral weight is removed from both the lower and the upper Hubbard bands, and it gets transferred into this quasi-particle peak, which disperses through the Fermi energy like so. And that's, again, reminiscent of this sort of cartoon picture that I drew here from the previous slide. So, this calculation, not surprisingly, sort of confirms the spectral weight transfer picture. But the other thing I want to point out is that this quasi-particle band actually has a dispersion associated with it. And the dispersive properties of this are really sort of inherited from the underlying non-interacting band structure, right? It's determined by a sort of a renormalized TT prime band structure in the calculation. This is going to be important a little bit later when we start looking at the quasi-particle interference. Okay. So, the take-home message from this, though, is we want to look for this spectral weight transfer, and we want to do it as a function of doping. And so the first question is how do I go about doping this monolayer system? So here, this is a nice idea that Hanno had. The idea was to take advantage of modulation hole doping schemes, basically the same thing that's done in the semiconductor industry to create two-dimensional electron gases and whatnot. So the idea is to take some heavily doped system, sandwich it together with some clean system, and let the mismatch in the chemical potentials transfer charge out of the doped system into your clean system. So in this monolayer system, the way this is done is essentially you take really heavily doped boron silicon substrates and then grow the monolayer on top of that substrate. And so the idea is that boron wants to pull electrons out of the tin monolayer, and that leaves behind a hole doped monolayer. And because it's a modulation hole doping scheme, it can do this in a very clean way without introducing a lot of defects into the tin layer. So this is very different from the way you dope sort of conventional oxides, for example, like cuprates.
Can I just ask another clarifying question?
Absolutely, yeah, no problem.
When you put dopants on silicon like phosphorus, you get orbitals which are very large compared to the silicon lattice. How big is the thin orbital in units of the silicon lattice?
So these the tin orbitals here are actually quite confined and oriented perpendicular to the surface. The boron orbitals that from the dopants, I'd actually have to go back and double check. I don't know.
Yeah, they are like 20 angstroms. The Bohr radius is like 20 angstroms. It's very large.
Yeah, so I mean, I think I'll show you some topographic maps later where look like there may be some indications of some boron states that you can see, but my main point is that when you do this doping scheme, you're not actually removing tin atoms here. So you're not disrupting the lattice in the same way you would in a substitutional dopant in like a cuprate, for example.
Okay, great. Thank you. Thanks.
Yeah. Okay, so fast forwarding through a lot of history, Hanno's group tried this for many, many substrates and for many, many years, and they were finally successful in 2017. So what I'm showing here, this is STS data, scanning tunneling microscopy data taken on a series of substrates or monolayers grown on substrates with increasing boron doping levels. Okay. So here, this is indicating sort of the dopant type in the substrate and the resistivity in the substrate. So increasing along this direction corresponds to what we should be increasing hole doping in the tin monolayer due to increased dopants placed in the silicon substrate. So STS, this is basically, this is d+id, so you can think of this roughly as the density of states of the system that's being probed. The state that you're seeing here at about minus 1.6 eV, this is a silicon band. The silicon gap would be covering from here to here on the 111 surface, and then this would be the first unoccupied silicon band in the substrate itself. The stuff in the middle here, these are the tin monolayers. Okay, so this is the lower Hubbard band. This is the gap, and this is the upper Hubbard band. And this is consistent with what the Werner-Hanke paper saw with the photo emission results, that you get this gap forming and spectral weight above and below the Fermi energy. And now as I increase the doping level of the substrate, what's seen is that there's a peak that sort of crops up or begins to emerge in between inside the gap, and it looks like the formation of one of these quasiparticle bands. And depending on how lovingly you look at this, you can argue that maybe some of that spectral weight is coming out of these upper and lower Hubbard bands. So here, Fang Fei actually tried to be a little bit more quantitative. He was fitting these lower and upper Hubbard bands and quasiparticle peaks with Gaussians to try to measure spectral weight. And what he found is that with increasing doping, the quasiparticle peak looked like it increased linearly. And this came at the expense of the upper Hubbard band, and the lower Hubbard band was a little bit more difficult to see as a function of doping. At least and that comes from overlaps basically of the silicon substrate or the silicon bands here with the lower Hubbard band. So Hanno asked me to compare this to some quantum Monte Carlo calculations, and so the next thing we did were DCA calculations on a triangular lattice. And so this is for a half-filled system. Again, we see a lower Hubbard band, upper Hubbard band, and a gap. And these are for the same parameters that came from Werner-Hanke's paper. So you can think of them as ab initio U's and J or T values or hopping values, sorry. And then upon 5% hole doping, we start to see the formation of this quasiparticle peak in between the gap, and it comes at the expense of the neighboring Hubbard bands. And this is again is sort of reminiscent of this cartoon picture that I drew for you earlier in the talk. And so this is sort of the first indication that we have that we're seeing something that looks like the spectral weight transfer that you would expect to have happen. Now, this is unfortunately not conclusive evidence. Again, we would have liked to have seen the lower Hubbard band, a more clear trend than the weight of the lower Hubbard band. There's also any number of reasons why you might expect states to form in the gap, right? You could imagine that there would be impurity states forming from the boron. Any number of things could be happening. And so this now comes back to the DQMC calculations I showed you. If this is really a quasiparticle band, we expect this peak to have a dispersion, right? There should be a dispersive state. And so the next thing we wanted to do is we wanted to check, is the system actually dispersive? Now, the immediate thing that leaps to mind is do photo emission, right? You can do an RPES experiment and try to measure a dispersive band. Problem is that in these dope systems, you can't grow films or monolayers of sufficient size to really do an RPES measurement. They're sort of on the borderline of nano RPES, but they're not quite big enough in order to do a photo emission experiment. And so if you want to do this, you need some other way to access the dispersive properties of the band. And the way to do that is actually with a technique called quasiparticle interference. And so this is a measurement that you can do with scanning tunneling microscopy. So I'm going to take a bit of a detour and talk a little bit about this technique, and then we'll come back to the system and look at the dispersions of these states. Before I do, are there any questions? All right. Yeah.
I actually want to ask, when on your plot, when n is 1, there is a little shoulder that looks like a quasiparticle peak, but cannot be a quasiparticle peak in the black curve. Why is that? What's this shoulder?
Yeah, so we see it actually here as well. And when we do the square lattice calculations, it looks like these lower Hubbard bands sometimes have these sort of precursor quasiparticle-like states here. I don't really have a good explanation for them, but we see them pretty universally when we do numerical calculations of the Hubbard model. These things are sort of the things that become, so I think what you're seeing here is sort of the equivalent of that on the triangular lattice. The exact position of this is probably dictated by the actual.
I think the single side DMFT would not give you this, but I think that some cluster theories, like dimer theories, there is some sort of a magnetic exciton peak or something like that, even in the insulating state.
Yeah, that may be the case. Yeah, I mean, this is a cluster theory, so this is a 3x3 DCA cluster in a mean field. Yeah. But yeah, we see it whenever we do these extended cluster calculations. Okay, so quasiparticle interference, just to remind you, when we think about itinerant states in a system, we're thinking in terms of block electrons, things with well-defined wave-like properties. The block states are eigenfunctions of the periodic lattice. But as you know, if you introduce impurities, the block states are no longer eigenstates, right? And you'll start to introduce scattering off of these defects. And so what can happen is you can have a block wave sort of propagating along, it encounters a defect, it'll scatter, and these incoming and outgoing waves are going to interfere with each other and create modulations in the density. And so, when you do this if these are block waves at the Fermi energy, these are nothing more, or the oscillation patterns that you create are nothing more than the usual Friedel oscillations that we teach in classes. What's important here is that, when you do this for sort of single free electron-like band structures, what you find is that the far field image, these wavelengths out here, these are really dictated by twice the Fermi wavelength. And this comes from the fact that you're dominated by backscattering processes where you go from KF to minus KF. And so the momentum change is 2KF. The reason I'm bringing this up is because these sort of far field images of these these quasiparticle imaging patterns, these actually tell you something about the underlying wavelengths of the electrons involved. And so QPI really sort of exploits this in order to image band structure and dispersions. So to show you an example of this, I like to pull this old paper from postdoc work that I did when I was at UBC. This is a scanning tunneling microscopy image of carbon monoxide atoms on the 111 surface of silver. And I like this example because it's a Shockley surface state in the 111 surface, and it's a very beautiful free electron-like band structure, nice parabolic band. You can describe everything almost perfectly with free electrons. So what you're seeing here, these parts that are grayed out, these are step edges, which have been removed from the data. Here, this is the carbon monoxide molecule, and here you see these rippling patterns. These are the Friedel oscillations, or the quasiparticle interference of the free electrons scattering off of these carbon monoxide molecules. So if you take a Fourier transform of this image, you get a nice 2KF image of the Fermi surface, right? This is the power spectrum, so this is telling you that the dominant wavelengths are really these 2KF scattering vectors in the problem. You can also do this as a function of bias voltage. So this is an image at the Fermi surface. This is a cut. So if I were to just cut along here, this peak here, that's what you're seeing here, that's this peak. And then as you tune the bias voltage up and down, you're basically just tracking the energy contour of the band, right? So as I move down in energy, the log K state shrinks up as the parabolic band closes. And so you just see a nice 2KF image of the band structure closing as you move down below the Fermi energy. What's nice about this technique is you can also go above the Fermi energy and you get access to the unoccupied states. So you see that here. And again, I really like this plot. always remember, I showed this once to a colleague of mine in Amsterdam, and he thought this was an ARPES image the first time I showed it to him. So you do really nice band structure characterization this way. So the idea is, we want to do these quasiparticle interference imaging to try to track the dispersion of this quasiparticle state in this tin monolayer system. So I want to talk a little bit about how we're actually going to model it first, and then I'll go through the details of the measurements and the calculations. So the idea is that we're going to introduce some non-interacting band structure. In this case, I'm just going to take the DFT bands that were calculated by Hanke's group. We introduce into the problem basically a single impurity. So some impurity potential U of R. In K space, it breaks translational symmetry, so you have a K prime argument. And we're essentially going to compute the interacting Green's function in the presence of this impurity, and then the imaginary part of that gives us the densities in the system. So the way we do that is with these sort of standard T-matrix formalisms. So the idea is, again, I'm after a Green's function. And so you can, like the slit experiment, I have to do coherent sums of all the ways the propagation can occur. So I have a term where the electron just propagates from K to K. I have another term where the electron propagates from K to K prime, but interacts with the impurity once, and then I can do that twice, and so forth and so forth and so forth. And formally, we can resum these into just this free propagator plus the scattering off of an effective potential, which we call the T matrix, which is just the sum of all of these possible scattering processes. You can turn this into equation form just following Feynman rules. So you wind up with a self-consistency equation like so, where you relate the dressed Green's function to the bare Green's function plus this T matrix. And you also get a secondary self-consistent equation, which involves the T matrix on both sides plus your impurity potential. So the idea is, if you know this impurity potential, you can calculate this self-consistently, get the T matrix. Once you have that, you can put it into here and you can get the Green's function. And that's basically all we do at this level of modeling. To simplify matters, this T matrix equation that I've written down here, there's many momentum arguments. And if you've worked with this equation before, you know that this can be quite challenging for an arbitrary impurity potential to actually evaluate this. So we make a bunch of standard approximations. The main one being is that I'm going to treat the impurity potential as a delta function. This effectively removes the momentum dependence of the impurity potential. And then if you do that, you can convince yourself that this T matrix actually becomes momentum independent, and you can just have a closed form solution, which is related to this momentum average Green's function, a non-interacting Green's function here. So this simplifies the algebra considerably. And so this is the approach that I'm going to be using in the simulations that I'll show you later. Okay, and yeah, as I said before, when you insert this into the expression for the dressed Green's function, we have a uniform part. This again just corresponds to that diagram where the electron just propagates through the system. Then we have the modulations due to the impurity. Once we have this, we can then do various Fourier transforms, and we can get this either as a function of momentum and energy, or in real space and energy as well. And just to show you what these look like, if you do this for a free electron gas, this is what the results will look like if I have a nice 2kF circular Fermi surface. The Fourier transform, or the power spectrum of the density modulation, is again this nice ring, very similar to the experiment I showed you on the silver surface. And then the real space modulations look like these Friedel oscillations, similar to those cobalt or carbon monoxide oscillations I showed you at the very beginning. And again, just because I like showing it, you can do very detailed simulations. So again, this is comparing to that silver surface state. You can grind through the algebra at various energies, and you can recreate the dispersions this way. And really link the dispersion of this feature back to the actual band structure. I'll just briefly mention these little other arrows I'm indicating. This is actually an electron phonon kink that you normally would only see in ARPES. And this little state that you're seeing here happens to come from the fact that these are unitary scatterers, not Born scattering. But point being is that we can, using this technique, we can sort of reconstruct what the band structure would look like. We can compare that to experiment. Now, that being said, this parabolic band, you might ask why I do this. This is a nice simple case where I can just look at this and see that this is the parabolic dispersion. In this tin system that I'm going to show you, it's actually a bit more complicated. The Fermi surface is large enough that you start to see a lot of Umklapp scattering, and the patterns become quite complicated. And so that's why we need the theory to compare against. So with that in mind, so again, I'm going to remind you, what we're trying to do is we're trying to confirm that this peak that's emerging is actually a dispersive state, and that it has a dispersion that can be linked back to the band dispersion of the tin monolayer system, and not, you know, some incoherent impurity state. So these are the experimental measurements of the quasi-particle interference. So again, this is a topography map. These are density images, and then these are the Fourier transforms of those density images as a function of bias voltage. Okay, so these are the experimental values here. This is, to remind you, is what the non-interacting Fermi surface should look like. And so here, this is in the doped substrate, the most heavily doped substrate. What we see is that there are these arcs in the quasi-particle image, or quasi-particle interference, that kind of look like a 2KF image of this Fermi surface. That's what we can actually link this back to the Fermi surface. There's also these dumbbell-like patterns. These are actually coming from Umklapp processes. Basically, if you replicate the Fermi surface around these Bragg peaks, these are where the arcs of the Fermi surfaces would be going. And so what's happening is the Fermi surface is large enough that you're starting to see some backfolding processes. And so it's a little bit difficult to deconvolve what the actual band dispersion is doing here. But nevertheless, as you sweep the bias voltage up, you can see that this guy starts to creep inward. And then you cross the Fermi energy at the unoccupied side, it pulls in even more. And when you go well above the Fermi energy, it almost flattens out and disperses even further in. So this is sort of the first empirical evidence we have that there is something dispersive happening in these peaks that are appearing in the power spectrum. And this is probably related to some sort of dispersion of the electronic states. Down here, these are calculations that are done in this T-matrix formalism using, again, this non-interacting band structure, and no other parameters have been adjusted other than the strength of the impurity potential. And here again, we see features that sort of look like what's going on in the experiment here. There's, again, this nice Fermi surface, 2KF type image, and then we get these triangular-like patterns forming from these Umklapp scattering. And they disperse in a manner very similar to what's happening in the experiment. They don't flatten out as much, and we think that that has to do with some many-body effects that we haven't included in the problem, but we do see some dispersion. To convince you of this, we can actually do this very systematically. So what we do is we take the quasi-particle, the experimental quasi-particle images, and we drop markers down on various features. So squares and triangles correspond to different features that we'll track. We put markers down on what we think are the corresponding features in the experiment. So for these triangles, you know, there's sort of two things we could identify, so we put them both down here. And then we track it as a function of bias voltage in the experiment, and we do the same thing with the theoretical band structure, and we compare the two. So that's what's plotted here. So the red dots are the dispersions of the experimental features, and the symbols correspond to the same features here and here, here and here, circle and here, and then the square and here. And then the black dots are what we get out of the corresponding simulation. Again, I want to remind you that I have not adjusted any band structure parameters in this calculation. I've simply taken the band structure predicted by DFT. I've adjusted the chemical potential to give me the filling that we think is in the system, and then just calculate it as a function of bias voltage. And we can reproduce, roughly reproduce a lot of the dispersion that we're seeing. There's some deviation here. Yeah, go ahead.
But doesn't this correspond formally to having quasi-particles with an effective mass being 1 in the bare mass? That there is no many body renormalization of the quasi-particle here in this version of the calculation.
That's correct. We haven't included any additional effects. So we think that some of that's going to cause some of the flattening of the dispersion, but yeah, we don't seem to see anything that looks like a massive band narrowing once the system is about 10% holdout. So, you know, this we basically argue that this is really evidence that this way, or this quasi-particle peak we're seeing emerge as a function of doping is really a dispersive state. And that's really consistent with the notion that it's the quasi-particle state that forms once you dope the Mott insulator. And it's not an impurity state. It's not coming from boron impurity states that show up inside the gap, or, you know, something happening to an impurity state in the tin monolayer, for example. So yeah, we argue that this was really sort of the evidence that this dope system, that the system could be doped and it behaved like a dope Mott insulator in the end, because we have the spectral wave transfer plus the dispersions. Okay. So the next question, obviously you start thinking this is a Mott Insulator, you've doped it, and so then the next thing you want to go look for is the superconductivity. So for the next 3 years, Hano's postdoc tried and tried and tried. Never found any indication of superconductivity on the STM that we have here. The STM out at JIME, where the lab is, only goes down to about 4 Kelvin. The postdoc, Fang Fei, gets a faculty position in China. He moves, gets access to a system that goes lower in temperature, finds the superconductivity. So that's what I want to talk about in the next set of slides. So this is now data taken on the most heavily doped silicon substrates, so where we have the largest amount of hole doping occurring in the tin monolayers. What's shown here is the densities of states zoomed in within the first 15 MeV of the Fermi energy as a function of temperature. So at 5 to about 4 Kelvin, you don't see much going on here, right? So this is to remind you, this is about where Hano's STM ends in temperature. There's a Van Hoff singularity sitting here, which again, we can link directly to a Van Hoff singularity in the non-interacting bands. And there's maybe some evidence of some sort of zero bias anomaly, but it's very, very weak. But in this new STM, they can go down low enough in temperature that you see really a formation of a nice gap and a sharp coherence peak starting to form at the lowest temperatures. Sure enough, if you apply magnetic fields, so now fixing yourself at 0.5 degree Kelvin and increasing in temperature, you can suppress this gap. So that's really indicating this is magnetic related or that it's superconductivity related. And then if you do zero bias maps in the superconducting state under a magnetic field, you start to see the vortex lattice forming. So the bright spots here, these correspond to regions of large conductance or large densities of states. So this is indicating a normal state region here, and this is a vortex lattice that you're starting to see form here. So great, superconductivity, and I think
what's the doping here?
We think it's about 10%. It's a bit hard to estimate because the only way we know for sure is by integrating the weight in the quasiparticle peak, and there's some uncertainty as to how to count that. You have to fit it with some Gaussians and then look at basically how much of that spectral weight is inside that peak. But yeah, we think it's about 10% hole doping. So then, yeah, the next question is then, okay, well, what's the symmetry of the order parameter? So one way to do this is to try to actually fit the spectra with various symmetries. So there's a number of options. This is theory model calculation now. What's shown in here in black is just the normal state density of states from the non-interacting band structure. And then the same thing if I put in a d+id order parameter in by hand with a magnitude that's sort of just a number that I put in by hand. What we do, we have this Van Hoff singularity which complicates matters. And so the way we're going to eliminate it is the standard trick of just dividing the superconducting and the normal state densities of states and comparing that. We'll do the same for the theory and the experiment. And when we do that, we get the dots that are shown here. And what we found is that we can basically fit this with whatever order parameter we feel like putting in. So we put in d+id, we put in s, whatever we put in, it produces about the same level of fit. And the reason for that is there's a broadening parameter, this Dyne's broadening parameter that actually ends up being pretty large. And that completely obscures all of the structure that's happening down here about it. And you can see it here from the sort of the width of these peaks and the relatively small value of the gap. It's only about 1 MeV. So it's quite challenging to just get it from fitting the STS data. We can't get any reliable indication of what the pairing symmetry is. And so we needed to look at other means to identify it. I will say again, we can fit it as a function of temperature, again, using multiple pairing symmetries. And so here what we find is that if we do this with a D wave or an S wave, we just differ in what the magnitude of the gap is. And that comes from the fact that the D wave has a 2 in the prefactor. So what you call delta, that changes, but the time or the temperature trace basically predicts a TC of about 4.7 Kelvin with some indication of a gap at higher temperatures, but with very large error bars. Okay. The missing data here, this is actually coming, there's some vibration in the system apparently at this temperature, so they couldn't get reliable data there. But we get or pretty reliably get a temperature of about 4.7 Kelvin. And that you can sort of see here at the 4.5 Kelvin data, you can see the sort of the beginning of a suppression of zero bias voltage here. So you can kind of see by eye the beginning of the formation of the gap at that temperature. Okay. So, the first thing we wanted to rule out was, BCS mechanism. We wanted to make sure this wasn't an electron phonon mediated superconductor. So as you probably all know, TC in BCS theory goes like, the characteristic phonon frequency multiplied by this e to the minus 1 plus lambda over lambda minus mu star. Mu star is a measure of the Coulomb potential. Lambda is a sort of a dimensionless measure of the electron phonon coupling, which you can think of as just a Fermi surface average of the electron phonon vertex. The TC that we get is about 4.7 Kelvin, and that's larger than what you would expect for bulk tin. Right? Bulk tin, I think, is about 3.3, if I remember correctly, 3.5 maybe. So this is maybe not so surprising that it's not so related to bulk tin, simply because the monolayer has a very different structure. Remember, the atoms are separated by much larger distances than they would be in bulk tin. And so this sort of indicated to us that what we really wanted to look at were not bulk phonons, but we really want to look at stuff associated with the monolayer. Fortunately, some people did the work for us. So this nice PRB, they went precisely for this system, for 1/3 of a monolayer of tin on the silicon 111 surface. They actually did the frozen phonon calculations and figured out what the vibrational modes of the tin are on this surface. So these are the dominant modes that they found. And most importantly for us, what they found is that this torsion mode that I'm showing here, so the tin atoms sort of moving these shearing motions, and what they call a wagging mode, where the tin atoms are sort of moving more perpendicular to the surface, these are the ones with the largest coupling, electron phonon coupling, according to DFT. So they, get a matrix element of about 50 MeV or about 13 MeV for both of these modes, and they're both at about 10 MeV in energy. You can put this into, you can estimate lambda by just taking g squared and multiplying it by the densities of states, essentially assuming that this g value is momentum independent, so it applies to the Brouillon zone. This predicts about a lambda of 1.3, and if you put that into the BCS expressions, you get this annoyingly large TC of about 10 Kelvin. We can also do Ellie-Ashberg calculations, again, assuming a momentum independent mode, and we come up with a number not too different from this. And this is for conventional or sort of standard value mu star, we made an assumption of. Now, again, this is sort of probably not a very reliable estimate, but it at least shows that it is conceivable that the electron phonon coupling could give you a TC large enough to explain the data. We don't think this is the case because, again, this mu star treatment is really questionable for a doped Mott insulator. If U is quite large with a narrow bandwidth, mu star is a very questionable thing to use. So we expect that this is probably going to be suppressed in the end by the Coulomb interaction, but at least a priori we couldn't rule it out. So then the next thing we wanted to look at was the unconventional mechanisms. And so, Andrei Chubakov some time ago predicted that these triangular lattice systems should have these chiral d+id superconductors. There's also this follow-up work that was done by Philip Huntsman's group, where they actually calculated a phase diagram, and they predicted that the chiral D wave should have the superconducting like dome as a function of doping in a triangular lattice Hubbard model. And so the next natural question was, can we go start looking for these sorts of order parameters in the system? So the first thing we did is, just to give you sort of a real space picture what this looks like. So the idea in these chiral superconductors is that you have sort of a nearest neighbor pairing, or you can have longer range pairing, but here I'm showing it for nearest neighbor pairing. Kuber pairs are really formed from one spin on a central site and then the neighboring spin distributed on the neighboring sites, with a phase factor which is given by this angle which winds by the 60 degrees as you rotate around. There's of course a number of different symmetries that are allowed. So this PRL actually outlines them all. So for D wave superconductivity, you have these sort of nearest neighbor pairing. You have this momentum structure plus this momentum structure. So this is the dxy, or x squared minus y squared symmetry. This is the dxy symmetry, and of course you get the sum of the two in a d+id superconductor. And to anchor ourselves, the nodes for this nearest neighbor pairing are shown here. They're shown here in the squares. There's a node at the gamma point, and then there are nodes sort of scattered along the Bragg planes of the Brillouin zone, or the boundaries of the Brillouin zone. Just to remind you, the Fermi surface is actually sort of arcing itself through here. And so in a lot of these cases, what happens is the d+id actually doesn't have a node sitting on the Fermi surface, which also helps explain why we had trouble distinguishing it from an S-wave case, because we actually don't have a node that appears in the Fermi surface. And so you don't expect the same sort of V in the density of states that you would get for a D-wave superconductivity in like the cuprates, for example. So, these are, of course, all the allowed symmetries. So we then went to DCA calculations to try to figure out what are the leading instabilities. And so this is work that was supported by our SIDAC project with Thomas Meyer. So just to remind you, DCA, you can think of it sort of like a cluster extension to dynamical mean field theory, but one that satisfies translational invariance. The idea is that you're going to take the infinite system and you're going to replace it with a small cluster that's embedded in a mean field, but it's embedded in such a way that the translational invariance of the cluster is satisfied. So the basic assumption here is that the correlations are short-ranged enough that they can be captured on the cluster, or at least the dominant correlations can be, and that the longer range stuff can be treated accurately at a mean field level. And the code that we're using, this is essentially the DCA++ code, which is developed out of Doran by Thomas and his group, using a continuous time quantum Monte Carlo solver. The reason we're using this DCA++ code is that over the years, there's been a lot of development effort put into measure sort of this generalized 4-point vertex function. So you can think of it as this diagram that I'm showing here. It's all the ways in which pairs of electrons can scatter by interacting via the Coulomb or the Hubbard U in the system, and all calculated non-perturbatively. So this can be measured with DCA++. The Green's functions can be measured with DCA++, and that allows us to solve the Bethe-Salpeter equation in the particle-particle channel. So loosely speaking, you can think of this as sort of a generalized BCS gap equation, where this is the general interaction between the Cooper pairs, and this is the structure or eigenfunction which describes the structure of the Cooper pair. Okay. In this formulation, the superconducting transition occurs when the eigenvalue of this Bethe-Salpeter equation hits 1. So that's when I take a Cooper pair, I interact, and I get back that Cooper pair again with no decay. And the symmetry of the Cooper pair can be extracted by looking at the momentum structure of this guy. So the important point here is that we can put in the band structure, we can put in the U estimates that came from the DFT calculations, and we can unbiasedly calculate what's the leading pairing instability in the system. And so when we do this for our problem, so again, we look at a 3x3 triangular lattice model. And what we find is that there's 2 degenerate solutions that have the same eigenvalue as a function of temperature. They're the leading eigenvalues. One corresponds to the x squared minus y squared symmetry. The other corresponds to the xy symmetry, dxy. So what's shown here, this is the phase of this pair function here, or the eigenvector, in the allowed momentum points in the cluster. The size of the dot is the strength of the eigenvalue, and the color is the phase, right? So this is, plus, minus, plus, plus, minus, plus, and so forth. And these calculations, these are done at a temperature that corresponds to about 77 Kelvin in real units. So because these are degenerate, what we actually expect to have happen is the solution is going to be a linear combination of the two. So it's a d+id pairing instability, or at least that's what what DCA is predicting is the dominant pairing instability in the system. And in this case, it's actually winning by quite a large margin at this temperature. So this is our, the first indications that for the band parameters that we think are relevant for the tin monolayer system, unbiased calculations of the Hubbard model tell us that d+id is really the leading pairing instability. And so that's the one we expect to have happen in the unconventional channel. So the next thing is we want to go now try to confirm this. So again, we tried to fit the STS, we couldn't do it. We tried, well, so far that's all I told you. So the next thing that we wanted to try was to look at the quasiparticle interference again. So QPI, when you're scattering superconducting particles, the QPI actually can carry phase information about the Cooper pair. And there's been a lot of discussion in the literature about how to extract this, but here we're looking at some qualitative features. So what's shown here in the top panel, this is the experimental data in the superconducting system as a function of temperature. As a function of bias voltage from minus 0.4 up to 0.4, and this is at a half a Kelvin, which is well below the superconducting transition. Okay, the images look a lot like what we saw before. Here's that 2KF image of the Fermi surface. Here's that dumbbell-like feature I pointed out to you. What's new is this star pattern that shows up right here at the center of the Brouillon zone. And this persists all the way through the superconducting gap whenever we're inside the coherence peaks and the bias voltages. If you warm the system up well above T or just above TC, these are dramatically suppressed, right? You can see they drop right out. There's very faint remnants of them sitting here. So this seems to indicate that these are related somehow to the superconductivity. And if you go well above TC, they disappear completely, right? So again, remember, this is well below TC. This is sort of just above TC, and this is well above TC. Those star patterns are disappearing. So they seem to be really tied to the superconductivity itself. And again, I'll remind you, this 5 Kelvin, this is right around the region where we had some evidence that there may still be some superconductivity, possibly fluctuating superconductivity. We're not really sure. So we then go simulate that to try to understand what's going on. And so I put in the d+id pairing symmetry that DCA tells us is the leading stability. And I just rerun the calculations and I look at what does the quasi-particle interference pattern do. So again, we get patterns that roughly look like what they look like in the normal state, but then I get the formation of this sort of petal-like feature showing up in here, sort of along these directions here. At zero bias voltages, they're suppressed again, even though the experiment shows it, but then at positive bias voltages, again, we see this flower-like pattern is still there in the theory images. If I put in an S-wave gap into the calculation and I repeat it, these disappear completely. So they are somehow related to the momentum structure of the gap. And so we know those flower patterns are at least inconsistent with an S-wave gap. We see them with this D-wave gap. The next question is the D-wave gap has some momentum dependence. The question is this related to the phase of the gap, or is it just related to the anisotropy of the gap around the Fermi energy? I can check that by just introducing the absolute value of the gap. So I just remove all the phase information by replacing delta with its square root of its modulus square. And what you see again is that these flower-like petals just disappear as soon as you do that. As soon as you remove the phase information from the superconducting gap, they vanish. And so, we can repeat this for all the D-wave or the longer range hopping d+id pairing, and we always get these petals appearing only when we have a chiral order parameter. If we put in any other order parameter into the simulations, these star-like patterns don't show up in the QPI images. And so again, what we think is that this is really evidence that what we're seeing is a chiral order parameter in the system. And this remnant that you're seeing above TC, this may actually just be because we have fluctuating superconductivity in the system. Okay. So right now, we're doing some other Hanno's postdoc or former postdoc is now doing some other measurements, specifically looking for edge states. So in these chiral d+id superconductors, you expect to have an edge state. So right now we're hunting for that, and this is why we haven't published this QPI image yet. But we think we have the DCA results combined with this QPI images. I think gives us pretty compelling evidence that it's really a d+id chiral superconductor. So with that, I want to just end, with some outlook and conclusions. Obviously, this is an unconventional superconductor, or at least if you are convinced by what I've shown you, on a silicon platform. So, obviously there's all the device physics. You can start thinking about ways to integrate this with silicon technologies. And this is, usually what we tell the people over at NSF when we're talking about this project. What I really like about the system, though, is that, as I showed you at the very beginning, it's a very clean system. So I know that some people in the audience have worked on QPI and cuprates. They've worked on tunneling and cuprates. In those systems, your tip is often having to tunnel through these rock salt structures in order to get to the copper oxide plane. So it's an indirect pathway for the tunneling electrons. And the QPI or the real space density images are often riddled with inhomogeneities. And there's been long discussions in the community of whether these are intrinsic inhomogeneities, but there's always a bit of concern that some of it may be coming from, stuff that's happening off plane, right? The impurities are off the plane, atomic structures that are off the plane, and so forth. This system, the tip gets direct access to where the superconductivity occurs. You don't have to tunnel through anything to get there, and you can grow it in very large, clean surfaces. And so, one of the things I'm really excited about is I think this system offers us a really unique opportunity to look at the fundamental physics of Hubbard models, or single band Hubbard models, without any of the oxide complications that we get in cuprates. So one of the things that we're currently thinking about is, are there substrates we can do this on where you'll get a square lattice instead of a triangular lattice, for example, and trying to get at Hubbard physics in that way. I'm hoping we'll find a system soon, and I'll be able to come back and tell you a bit more about that. All right, so with that, I'll wrap up. So as I said, I hope I've convinced you that the third of a monolayers of tin grown on silicon, that these really behave like single band Mott insulators on triangular lattices. I've shown you that these can be hole doped using modulation doping schemes, and this gives you sort of really clean doped Mott insulators. We see spectral properties that are consistent with unconventional superconductivity. And the combination, I think, of the DCA simulations and the QPI measurements is giving us a really strong indication this is really a chiral d+id topological superconductivity. And so with that, I will stop and take any questions you might have.
Thank you, Steve, for a very nice talk. Very self-contained experiment and theory all together. So, do we have any questions from the audience? Please feel yourself free to unmute.
Can I ask a question? Actually, two questions. Yeah, thank you for a very nice talk. I'm curious about the d+id superconductor part. Can you comment on the relation to the Van Hoff singularity? Because I remember the paper you cited, you mentioned Tubakov's paper is due to the Van Hoff singularity. And also I'm curious about the how can you confirm this edge state experimentally? Do you measure imagine measure in the heat transport or something?
Yeah, so I can comment. So the role of the Van Hoff singularity, I'm not 100% sure on. This project is actually where I started getting interested in these chiral superconductors. So I haven't worked on it too closely, or other than what I've shown you. We haven't done very systematic calculations, at least, to look at, we can imagine tuning band parameters and moving the Van Hoff singularity below the down and looking at how the superconducting correlations evolve. The issue with that is these calculations are incredibly expensive. We burned a lot of time on Summit in order just to get what I showed you. And so, it'd be a very expensive project to do. So we haven't done it yet. So I can't really comment on how important the Van Hoff's position is for that in this case. I know in Chubakov's paper, he talks a lot about, he mentions that the Van Hoff plays an important role. In terms of the experiment detection of the edge states, the strategy we're looking at right now is the regions are small enough that we can find the edges of them. And so we're trying to find, actually just go measure the zero bias state there and look at it, how far it penetrates into the sample. Because my understanding of these systems is that the penetration of that edge state should go like 1 over the superconducting gap. So as you warm up towards TC, you should see that edge state penetrate further into the system. And so we're looking for that edge state, and then we're going to try to confirm the temperature dependence as you warm up, and see that it actually does penetrate further and further in.
Okay, thank you.
Any other questions? So some quick clarification, just to make sure. This is our plain vanilla Hubbard model on the triangular lattice, right?
Single band Hubbard model on triangular lattice, yeah. The hoppings, it's got there, at least according to the DFT calculations, the hoppings are long range. You have to go up to 5th nearest neighbor in order to get the band structure right. But yeah, there. Other than that, it's a single band Hubbard model.
And how do you take care of this long range hopping and the DCA calculations?
So we actually truncate it at when you reach so we only go up to 3rd nearest neighbor hoppings in the DCA calculation, because our clusters are, that's the longest range hopping the cluster can actually support. Otherwise, you start double counting the long range hopping.
Right. Any other questions?
I would like to ask some questions, but I'll let others ask first because I asked already too many questions.
Okay, let's wait a minute for anyone. I would say, Vlad, you can go ahead.
Go ahead. Yeah.
So Steve, it was very interesting talk. I thank you very much. This was kind of an eye opener. This is really a beautiful system, and so my question is concerning the QPI story. So one of my interests over the years has been the what happens when you put impurities, but not in non-interacting systems where you get standard Friedel oscillations, but in correlated systems near Mott transition where quasiparticles can interfere. So, and that partly was kind of stimulated by previous work done by Nandini Trivedi's group and collaborators, which was of relevance to Seamus-Davis experiment, where they discovered originally a phenomenon called something that they describe as healing. And so we have done some related work in the normal phase, but it boils down to the following. Basically, when you put a particle somewhere, normally you send Friedel oscillations which decay slowly, as you explained. But as it turns out that when you self-consistently calculate the renormalization of the quasiparticles, so basically there's an induced potential that's actually created by interactions around the impurity. And that can actually suppress the perturbation that the impurity creates in the electron gas to some modest region. So there's actually, apparently, if you just do single site type of DMFT in real space, and they have that, which is a version of this is the Gutzwiller type of calculation, which you can also do in the superconducting phase. Then you find that this, for example, a superconducting order parameter will be affected by the impurity, but only very close to the impurity, as opposed to getting these long tails, which you would expect, for example, if you have D-wave nodes and so forth. So they made a big deal out of this. Apparently, this is a scene in Seamus-Davis experiments where you really, near the Fermi energy, you see images which are very flat. And if you just do Bogoliubov de Gennes without this quasi-particle normalization, then you really get a lot more inhomogeneity. So what we found is that actually there's a very similar effect in the normal phase, and the same type of healing kicks in actually relatively close to the Mott transition. So it's a many-body effect. Now I wonder. So if I understand correctly, the QPI procedure is basically you calculate the scattering, a full scattering from one impurity,
yeah,
and you assume that the cross terms are negligible because these are weak impurities or dilute impurities or something like that, right?
Dilute, yeah, that's the assumption.
So if you can solve the same one impurity problem, but in presence of strong correlations, that would tell you something. And the question is, why do you think that this is? It seems to me that the results you've shown, which is obviously the first thing that you do, is to just try a non-interacting type of time binding model or band structure. Then you put one impurity, you do the Friedel oscillations, and you get this pattern. But let's imagine that if you have strong correlations, that this one impurity scattering is dramatically modified now, or there is this phenomenon of healing. So my question is, in this material, I understand that people have done extensive Hubbard model calculations, DCA, and so forth. So there are two questions related to that. The first one is, how important are the cluster corrections? Because in some materials like or Mott organics, which are also on the triangular to the quasi-2D lattice, it seems that the cluster corrections are not so big, and that a lot can be explained through ignoring cluster corrections to the single site version. Second question is, how large are the renormalizations? For example, the quasiparticle weight, is it of order 1, or is it something much, much smaller than 1?
So I should know this number. I should know this number off the top of my head, and I don't have it on the tip of my tongue.
But isn't this on one of your slides where you estimated the weight for the quasiparticle weight from the just fitting Gaussians? I thought that there was some.
So that's experiment. Yeah. So this is experimental.
But should we think of this as estimating the quasiparticle weight, or?
Well, it's the doping level, right? So the number, the total integrated spectral weight should go like 2x, where x is the doping in the system. So when you integrate this band here, if you introduce X carriers into the system, the weight of this should go like 2x, is my understanding.
Isn't there a relationship between that and the quasiparticle weight also? I think that quasiparticle weight will also go as 2x. That was my impression. Anyway, I'm not sure about this. So what is your feeling? Is this a system that will be strongly correlated in this regime, in the sense that the effective mass should be substantial, that the quasi-particle weight is significantly smaller than 1. That's why we'd expect these healing effects on QPI to be significant.
Yeah.
But if Z is close to 1, then probably doesn't matter. So what's your feeling about that in this system?
Well, so what I can do is I'll dig out the Z values we actually get from the DCA calculations. I'll give you some hard numbers if you let me get back to you on that. But my suspicion is they're actually going to be pretty small, or it's going to be close to 1. And the reason why, and I actually found this quite surprising, is that the dispersions of these quasi-particle states actually agree fairly well with what we get from just the non-interacting band. Right? We don't.
So somehow,
the states nearest the Fermi energy don't seem to be renormalizing significantly, with the exception of these peaks here. These contours get flattened quite a bit relative to what's seen in the calculations. The calculation here is predicting that you have these triangles that are warped, but the experiment's seeing a very strong flattening of these triangles. So
how is this even possible? You know, if you have a doped Mott, if this is really a Mott Insulator, you put 10% doping. How can that be weakly correlated? That it's very hard to believe this. I mean, I don't know. Maybe there are things that are missing, but it just seems to me like, for example, you know, in Mott organics, which are also triangular one-band model, and they've seen some superconductivity, but you can directly measure the Fermi liquid temperature, coherence temperature, the quasi-particle weight using different ways, including optics. And there are substantial renormalizations, you know, in those materials. These are real material. I'm not talking about theory. So I wonder, how can it be that this is a weakly correlated in this regime?
Well, it's certainly, I mean, it's looking like it's weakly correlated near the Fermi level. I don't know what's happening with the overall bandwidth. So I don't know how momentum and energy dependence this is. I agree with you, it's surprising.
Right. But I do find it very interesting because, you know, I wanted to, so I put actually in the chat a reference to some of the earlier work we've done where we carefully treated this one impurity in a correlated host. Okay. And we find substantial effects. Now, you know, I was always dreaming about the possibility that STM can look at this. Unfortunately, most models where they do STM, they are either multiple band models, or they have all the complications of oxides that you talk about, or there is always something on the Mott organics that cannot be done. So it's not a single band model. And there's a million reasons why it was impossible to find a simple setup where you can do a single band model with correlations and test these ideas. So maybe this is the first system where one could actually study this by maybe more carefully looking at the, you know, I mean, maybe one needs to do a little bit more precise analysis of these QPIs and maybe change the doping level more, or, you know, something else. But it seems that this could be an ideal system to actually ask, you know, what is the correlation effect on QPI and not just the, you know, the weak coupling picture of QPI. Yeah,
no, I absolutely agree with you. And I'd like to talk more about that at some point if you have chance.
And for those that haven't noticed, Vlad just posted a link on the chat window. Thank you, Vlad.
Thank you.
I'm actually looking at the paper right now.
Yeah. I'll grab it at the end of the talk.
What's surprising is that, you know, we found, at least at that level of theory, which is the, you know, single side good filler type of theory, that this is a surprisingly large effect. And this is what Nandini et al. Also claimed for, that for cuprates, this is not a small effect, that there's a gigantic healing effect, you know, that in basically the induced potential is very localized. And Weiku has done some similar questions at the level of DFT, where you actually do supercell, you put an atom and ask, what is the effective potential of an atom? Is it, you know, how non-local it is? And the Friedel picture would tell you that it's very non-local, because there's always, you know, in real materials, DFT has interactions. So, but there is some sort of healing even at the DFT level. So this is actually not fully understood, I think. You know, to what extent is this induced potential local or not local, and to what extent the non-interacting picture actually breaks down in real materials. And so I think it would be very nice to see some very careful system on model systems like this, which are simple enough where this can be really, you know, extracted and not masked by complexity of band structure and many details that you come in your way.
Yeah, we've got some doing some analysis of what's happening near the impurity in real space. We were also trying to look at. We haven't finished the analysis yet. There's one of things on our list of things to do.
Okay, well, you know, if you have some thoughts about, I mean, you know, we've been doing this work for many years because we wanted to see why is the disorder-driven transition, disorder affecting Mott transition, and other things. But I mean, if there's a follow-up, we can maybe talk some other time. And
Sure,
but,
yeah, that'd be great.
I didn't know about any of this, and so I find it really very stimulating. It's great line of work.
Well, if NSF funds us, we'll hopefully go chasing after a square lattice version of this.
Right,
well, it's
right.
nice that you beat the condensed matter, the quantum optics, the AMO people into studying the Hubbard model and the triangular lattice. So I know these samples are very tiny, but is there any chance to do something like phase-sensitive experiments, like with build a tiny squid to measure the symmetry of the order parameter?
I certainly think it's possible. I don't know. So as I said, the sample are getting on the verge of nano-ARPAS length scales. So we could think about doing ARPAS. That's not phase sensitive, obviously, but I think if you wanted to start doing squid measurements, I think it would just be a matter of getting the samples out of the chamber where they grow them and then into the squid. Right. Yeah, I don't see any reason why not. No.
You can maybe. All right. Yeah, but it's tricky, right?
Yes, I said these things. The sample, or at least the silicon system, I think it's around 100 or so Kelvin or so. You start to disassociate the tin atoms from the monolayer, or from the silicon. Sorry. So everything's got to be sort of grown in situ and then done at low temperatures. So they grow them and move them into the STM and do the measurements. But yeah, I think they've got vacuum suitcases. They should be able to get them out. Yeah.
Any other questions from the audience? All right. If not, let's thank Steve one more time for a very nice talk. Thank you so much for sharing your work with us.
Thank you.
And we invite you everyone to join us again next week. The announcement will come on your mailbox. All right. Have a great rest of the week.